All right, so we're going to continue with section 14.1. And first, one note that we'll need for our first example is that if f is greater than or equal to 0 on R, then the volume, capital V, of the solid region between the graph of F and R is V equals the double integral over R of f of x, y with respect to area. All right, so you can look at the picture that we drew at the beginning of the notes of our function of two variables f of x, y over some region R, because we drew a positive function there. And if you would just imagine the volume between that function and the region, this integral will compute that volume, but it only do it for a positive function or a non-negative function. All right, so now with that, let's look at number 40 on page 911. So page 911, we're going to do number 40. So I apologize, I'm starting off with a problem that's kind of later in the numbering and a little more difficult, but there are a lot of examples. There's a lot of material that we kind of need to cover, and this example will give us a good mix of things all in one. All right, so in exercises 34 through 44, find the volume V of the region using the methods of this section. So when it says the solid region bounded above by the parabolic sheet z equals y squared, on the sides by the sheet x equals 1 minus the quantity y minus 1 squared, and the plane y equals x, and on the bottom by the xy plane. So for problems like this versus you trying to like put all those things together in your head or draw all of those things, what I'll do is give you a way to kind of set things up to help you set up your integral, because we need to get to an integral. So you want to kind of know the top, the bottom, and the quote unquote sides. So the top is going, and they tell you above or below. So the top is z equals y squared. The bottom is z equals 0. So these two things, the top and the bottom, those things give us our integrand. So we're going to write over here integrand, or what's inside of the integral. They don't determine our bounds. So then the sides, or the quote unquote sides, we don't have. So the sides are given by the two functions x equals 1 minus the quantity y minus 1 squared, and the other function was y equals x. Those are going to give us our bounds for our integral. So now with the sides, what we're going to have to do is you're oftentimes going to run into having to find the intersection of these two things. And really what I want to do is we want to always sketch our bounds. Remember I said we always want to sketch our two-dimensional region. So I'm going to want to sketch both of these. So I could just dive in and sketch them. But I know I'm going to need some constant values and set them for integral, because all of our integrals have some constant values in there, and we don't have any constants swimming around in our bounds right here, right now. So we'll take this we'll take this x equals y, and we'll put that in right there. So we get y equals 1 minus the quantity y minus 1 quantity squared, which gives us that if we solve this, we're going to get y equals 0 or y equals 1. When you go through and do that. Now what I'm going to do is I'm going to sketch this region. So I'm going to sketch that, and I'm going to sketch that. And if you're not sure how to sketch them, I mean, this is the same as x equals y squared. And then this is going to give us a shift. That's going to give us a flip, and that's going to give us a shift as well. So, but if you're not sure how to sketch something like this, just put it in Desmos, and you can just have that sketch it for you, and then sketch it on your paper after that for your own sake. So here, and remember, we're sketching the region over which we're integrating is what our sketch is. So we're going to have the 0.11. I'm going to kind of exaggerate this a little bit because we're going to have a parabola that looks like that. And I didn't sketch this big enough. I should have sketched it a little bit bigger. And we're going to have the line y equals x. So this is y equals x. And this parabola is x equals 1 minus the quantity y minus 1 squared. Our region is this little thing right here. So now we need to look at that region and determine, is it a type 1 or a type 2 region, figure out how to set things up. So remember, type 1 is going from constant to, from function to function in the y direction. So we would be going this function up to that function. Now, and then type 2 is going from function to function in the x direction. This is both type 1 and type 2. We could go from function to function, which would be y equals something to y equals something. So here we have that's y equals x. Down here, we would have to solve this for y. So we don't want to have to do that. So instead, let's go in as a type 2 and go from function to function in the positive x direction. And then we already have this is x equals y, and this is x equals 1 minus y minus 1 quantity squared. So notice some regions are both type 1 and type 2. This is both type 1 and type 2, but the nature of our problem kind of dictates that we should probably just go this way. Let's get a little arrow in there. Go in that direction, in the positive x direction, and do this as it is type 1 and type 2. So we'll write that down as type 1 and 2. But what are we going to do? We're going to do it as type 2. We'll do it that way because everything's already set up for that. So I always said to sketch and define your region. So when I say define, I mean you write down r equals the set of points x comma y such that, all right, so we have our functions, but what about our constants? Constant to constant. So what is this constant? We can get that information from right here. So from y equals 0 all the way up to y equals 1. So we have our constants right there as well. So if we do this as a type 2, everything's already set up nicely for us to do. We can do it as a type 1. You just got to do a lot more algebra. So y goes from 0 to 1. Then x goes from this line, which is y, up to this curve, which is 1 minus the quantity y minus 1 squared. 1 minus the quantity y minus 1 squared. And the reason I say to always write this out is because then you can easily see the bounds for your integral. Constants are always going to go on the outside, so we're going to go from 0 to 1 on the outside. Functions go on the inside integral, so we're going to go from y up to y 1 minus the quantity y minus 1 squared when we set up our integral. So now we have the integral, the iterated integral, from 0 to 1. And then from y to 1 minus the quantity y minus 1 quantity squared then of our function. So now we need to look at our function. So that's what I said was going to be your integrand. So in your integrand, we're doing, you're going to end up doing top minus bottom in here. So I told you your top was z equals y squared. And the z indicates that that's kind of our top and our bottom, but we're not going to include the z in there because we're doing everything in terms of x on y. So we're going to do y squared, your top, minus your bottom, which is 0. And then now these have y's in them. So that tells me this needs to be dx. And then after that, I'm going to integrate with respect to y. So now what I'll do is I'll get you through until we're at the calculus 1 part. And then once we get to the calculus 1 part, I know you all already know how to do that. So let's get over the calculus 3 part first. So we always do the inside integral first. So that 0, 1 integral will stand out there. Now we're integrating y squared with respect to x. So when we integrate with respect to x, the y terms are treated as a constant. So this is the integral of a constant with respect to x. And what you get when you integrate a constant with respect to x is you get that constant times x. So we're just going to have x times y squared, and then it's a definite integral from y to 1 minus the quantity y minus 1 squared. From y up to 1 minus the quantity y minus 1 squared. Remember, you were integrating with respect to x, or just keep in mind this is x equals and x equals. So now in plugging in your bounds, oops, let me put my dy out here because we still haven't integrated with respect to y. Now, when you plug in your bounds, you integrate it with respect to x. These bounds need to go in for x. Or just keep in mind that's x equals y and x equals 1 minus the quantity y minus 1 squared. We're not going to touch that constant right there at all. We don't need to do anything with that. So now this equals, we can fit this here. This equals the integral from 0 to 1 because we haven't integrated with respect to y yet. Put in your top bound first. So when I put in my top bound, I would end up with, or actually I'm going to factor out my constant to save us a little bit of space. So this is just y squared. Then I'm going to put in my top bound to that x. So we end up with 1 minus the quantity y minus 1 squared. Put that in for x minus, put in my bottom bound, excuse me, minus y, close that, and then dy. So now we're at a calculus 1 problem. Now I'll let you all finish that off from there. So you would just simplify this integrand. So multiply this stuff out, and then you can just integrate that with respect to y, put your bounds in, and you're finished there. All right, so next we will look at number 32. This is the next problem I want to look at. Number 32 says, in exercises 20 through 33, express the double integral as an iterated integral and evaluate it. All right, the double integral over R of, the double integral over R of something 2y dA. And then they describe our region for us. They say R is the region between the graph of y equals sine of x and the x-axis. So it's between the sine graph and the x-axis, but then on the interval 0 to 3 pi over 2. So this is one of those problems where you can kind of see why you always need to sketch your region, because you may be misled into thinking, okay, well, it says on here that R is the region between y equals sine of x and the x-axis. So we would go from y equals 0 to sine of x, and x will go from 0 to 3 pi over 2. But that will give you, that would be incorrect if you did that, just because of the nature of the sine graph. So let's sketch our region. All right, probably should have, let me give myself a little more space to work with here. All right, right, so now, so sine, let's see, put pi right here, and then 3 pi over 2, I'll put right here, and then pi over 2, be right there. All right, so sine now is, we'll make one like right here. So then our curve, our region, excuse me, over which we're integrating. Put this about here. So that's the region over which we're integrating right there. Oh, wait, so now, remember we have to figure out is this a type 1 or type 2 region to even set up our problem. But now type 1 would say we go from function to function in the y direction. But we have a little bit of difficulty because the region itself is that, because it said between y equals sine of x and the x-axis. So that's the region. So we can't go from function to function and get from, like, say here to there or something. So we really have two regions. We're going to have to split this up in that region and this region and then sum the two integrals. So this first region, is it function to function in the y direction or function to function in the x direction? So it's function to function in the y direction. If we tried to go in the x direction, you would run into, you were going from this function to that function right there, but then you would have to go from constant to constant. So here, it's set up very nicely to go from function to function in this direction right there. So I'm going to draw my arrow there. We're going to call this region R1. And then same thing here. You could do either one. If you could do, if you wanted to go from constant, from function to function that way. But we're going to just do, set this arrow like that. And we'll call this R2. So we now have our two regions. We're going to define our regions. R1 equals the set of points x, y, such that you always want to set up your region. So actually, let me explain a little more detail. So this is of the form y equals sine of x. So that also would tell you, like, I don't want to solve this for x because I'm going to have some inverse trig function. So I would certainly want to go from y equals 0 to y equals that. I mean, the way they worded the problem as well kind of indicates that as well. You don't want to have to figure out what this is a function of x and that is a function of x. Is a function of y and a function of y. So now for R1, we're going from constant to the constant. We're going from on the x to the left is x equals 0, and then x equals pi. So x goes from 0 to pi, and then y goes from 0 up to sine of x. And then for R2, that equals the set of points x, y, such that x goes from pi to 3 pi over 2. Oh, sorry, let's write what these are. These are, so R1 is type 1, R2 is type 1. All right, sorry, where was x? Oops, that was not 0, that was supposed to be pi, wasn't it? Yeah, that was supposed to be pi to 3 pi over 2. Pi to 3 pi over 2. And then our y here, now in this scenario, where's our y go from? This is y equals sine of x. So we're going from y equals sine of x up to 0 this time. So this is switching the order. Sine of x up to 0. So now we can set up our iterated integrals. So the double integral over r of 2y with respect to a equals the double integral over r1 of 2y with respect to a1 plus the double integral over r2 of 2y with respect to a2. And this equals the integral from 0 to pi of, and then from 0 to sine of x, 0 to sine of x of our integrand is 2y. This has x in it, which tells me that's dy right there. And then that has to be dx. And plus the integral from pi to 3 pi over 2. And then from sine of x to 0 of 2y. These have x's in them. So that tells, well, this has an x in it. So that tells us this is dy and then dx. All right, and then from there, I'll just go through the first part to get us out of these iterated integrals and get us back to calculus 1. So this equals the integral from 0 to pi of, now we're integrating 2y with respect to y. So that's just going to give us y squared. And then from 0 to sine of x. And then dx, because we still have to now integrate whatever this is with respect to x. And then plus the integral from pi to 3 pi over 2 of, same thing we'll get here. We'll get integrating 2y with respect to y. We're going to get y squared. But now our bounds are from sine of x to 0. And then we have to, whatever we get here, integrate that with respect to x. So we'll go ahead and substitute these in. And remember, this is a y equals, or just go back and look, I integrated with respect to y, which means I need to be plugging that in for y. So that equals the integral from 0 to pi of sine squared of x minus 0. Sine squared of x minus 0, and then with respect to x. And then plus the integral from pi to 3 pi over 2 of 0 minus sine squared of x, so negative sine squared of x with respect to x. And then for these, you can just use, for each one of these integrals as a calculus 1 integral, you would just use the double angle formula. All right, so I'll stop this video here, and that'll conclude section 14.1's lecture video. But I'll try to either post this supplementary video with some more examples, or I'll send you all some examples via Elms that you can go on, just since I only got time to finish 2 examples during lecture. But make sure you ask some questions of your TAs in discussion, and then also me in problem sessions about section 14.1. Oh, there's one last thing I did want to mention, is that you can use for exercises 51 through 56. Given a region R in the XY plane, the area of R is given by a equals the double integral over r of 1 with respect to a. All right, so if you need to find the area, your integrand is just going to be 1, and then you just set up your bounds based upon whatever your region r is. You can find the area of that region. All right, so that's the last thing that I'll mention in this lecture.